Hi, my name is Raymond Su. I've been in the optimization industry for several years, in the operational research and AI industry. I've recently came across this algorithm, linear regression, from data science and machine learning, and I find it very interesting. And I think I've connected the two technologies together. Uh, and today, if you're like me, coming from the operational research, and you're very familiar with technologies like CPLAX, solvers, mixed integer programming, and stuff like that, whether you use Ames or Quintic or whatever platform you use to build your solvers, um, I hope I'll show you how do you actually build a linear regression, a multi-linear regression solver, and yeah, hope it helps you in understanding how the algorithm works from the machine learning industry. So, um, I'm going to start with this data set here that I've quickly Googled for sample data set on multiple linear regression. So we look at the health data here. We're trying to predict the death rates of 1,000 residents, looking at the doctor available, the hospital available, and the uh, you know annual per capita income and the density of people. Right. So this data set I've downloaded, uh, I'm just going to take like the first 10 example from it, paste it on a Google Sheet. I can just show you again. I've done it before. Basically, you start with this data, and you first of all, you're trying to predict x1 here. So this would be your predicted value of x1. This would be the error, and we want to measure the squared error. And I'm going to put the list of coefficients here. So since x1 is what we're trying to predict, so we only have coefficient for x2, x3, x4, x5, and a constant. So to calculate the prediction of x1, we assume that we take the coefficient of x2 multiply with x2 value here, plus the coefficient of x3 multiply with value of x3, plus coefficient of x4 multiply with value of x4, plus coefficient of x5 multiply with value of x5, and then plus the constant. Now, what are our decision variables? In this particular case, our for linear regression, right? Our our decision variables are basically the coefficient, but also the errors, because the errors are actually what we're trying to minimize. So we can define our objective function here, which is indirectly related to our decision variable of errors. And these are basically the squared error. You can just make them square of the error, power of 2, populate that. Now the objective is basically to minimize the sum of error. I'm going to color the objective green. All right. So you can use multiple different solvers. So I don't have any licensed software because this is my personal laptop. So I recommend using OpenSolver, but you could use any kind of other solvers. You can get them from the add-ons of Google Sheets. So just type keyword solver, and you'll find a lot of different types of solver that is available in Google Workspace Marketplace. So I recommend OpenSolver because it's simple. So let's have a look. So let's open the sidebar for OpenSolver. So first of all, our objective function is to minimize the sum of the square error. That's the algorithm of linear regression. And our decision variables are the coefficient as well as the error. Okay. So to model the constraint, OpenSolver only allows me to select two values, which is kind of limited. So what I'm gonna do here is I'm just gonna create a new column um, over here, which basically is the predicted x1 plus the error. So this would be our constraint. So this is basically this plus this. Okay. Let's populate that. Okay. And error values. So our constraint is this column must be equals to what we're trying, the actual value, right? So the error plus what we predict must be equals to the actual value. And we have to repeat this multiple times. So this is why I only pick a subset of the sample data, because it's quite tedious if we were to model this in a spreadsheet. But of course, if you have more advanced licensed software of solvers, you can automate this part in a script, and then it would not be that difficult. So basically, for linear regression, every single data point is actually a constraint in our linear programming solver. G6, G7, 2, 3, 4, 5, 6, 7. Oops. And then 8. Oh, I made a mistake here. I have to click this. So, okay. And G9 equals to A9. Oops, I missed one data point. 2, 3, 4, 5, 6, 7. Yeah, I missed the number 8. I picked the wrong one. Something's not right here. It's not adding a new one, so let me try it again. It's G8 must be equals to A8. Save. Oh, I should click new, add new constraint, of course. Okay, so seems like it's overriding my previous constraint. Just do it again. No biggie. Alright, and it is done. 9. And then the last one. Okay, so 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now we have all our constraint. We can try to click solve. So if you use it out of the box, the OpenSolver, linear solver will try to check for linearity. And usually linear regression isn't really a linear model, so you can't really run it for linear. So I'm just going to uncheck this check mark and click solve again. And there it is solved. It has minimized the objective function. These are the coefficient value. These are the error. And these are the predicted value of x. So you can see these three have no error. These two has no error. There's some slight errors in this first and second data point. And yeah, that's about it. So there you have it. So that's how linear regression works from a linear programming solver perspective. Oops, I noticed I made some mistakes there. So this is not correct. Just gonna change it and rerun it again. See if it improves the model. Yep, so that's more like it. So we have a better model here, and yeah, so we have some errors here, but it's basically minimized. Okay, so that's how a linear programming solver, or rather a mathematical programming solver, can actually build a machine learning linear regression model.